Today, we're going to talk about a group of molecules that are, well, they're basically hiding in plain sight, but they're doing some of the most critical jobs in our daily lives. They are truly the unsung heroes of modern chemistry. So, let's start with a little bit of a puzzle. What does, say, the Benadryl you take for your allergies, the Novocaine that numbs your mouth at the dentist, and the brilliant colors in your clothes, what do they all have in common? I mean, on the surface, they seem completely unrelated, right? But they all share a secret chemical connection. Well, the answer is this fascinating class of organic compounds called amines. These molecules, they're the common thread. They are the essential ingredient that makes all of those incredibly diverse products possible. And today, we're going to pull back the curtain and see exactly how they do it. So, just how widespread are these chemical heroes? Well, it turns out they're not just some niche ingredient for a few specific things. Nope. They are fundamental building blocks in nature, in medicine, and all throughout industry. I mean, the applications are just staggering. In our own bodies, they form the very proteins and hormones that keep us going. At the pharmacy, they're the backbone of crucial drugs like adrenaline and antihistamines. And in industry, oh man, they're used to make everything from nylon to dyes to cleaning products. The big takeaway here? Our world would look and feel very different without them. Okay, so to understand what makes amines so incredibly versatile, we need to get to know the family. And just like any family, they all share a common ancestor, one that defines their core identity. And that parent molecule is ammonia, NH3. It's a really simple structure, just one nitrogen atom bonded to three hydrogen atoms. That's it. Every single amine you'll ever encounter is just a variation of this blueprint, where one or two or all three of those hydrogens have been swapped out for something a little more complex. And here's the secret to their power. You see that unshared pair of electrons just sitting on top of the nitrogen atom? That lone pair, that's the source of their whole chemical personality. It's what makes them reactive, it's what makes them basic, and it's why they can do so many amazing things. All right, let's meet the children. First up, we have primary amines. This is what you get when you swap out just one of ammonia's hydrogens for some kind of carbon-based group, what chemists call an alkyl or aryl group, which we just represent with R. Simple, elegant, and super useful. Now swap out a second hydrogen, and you get a secondary amine. Here, the nitrogen is bonded to two of those R groups and just one hydrogen, so we're building up in complexity, right? And with that, we start to get different properties. And finally, if you replace all three hydrogens, you've got yourself a tertiary amine. There are no hydrogens left on the nitrogen now. It's fully substituted. And this is the type of amine you'd find in that Benadryl we talked about right at the beginning. So how do we actually talk about them? Well, chemists basically have two main systems. The common names are pretty straightforward. You just name the group attached and add amine at the end. But the official system, the IUPAC system, is a bit more precise. So, for example, what most people would call ethylamine is officially known as phenamine. Okay, so we know what they look like, but what do they do? Well, the most important chemical property of amines comes directly from that lone pair of electrons we keep mentioning. It makes them basic. And here's the key concept. A Lewis base is just anything that can donate a pair of electrons. And that lone pair on the nitrogen atom, it's just sitting there ready and totally willing to bond with a proton from an acid. This ability to accept protons is the definition of basicity, and it pretty much governs all of their reactions. But here's the thing. Not all amines are created equal. This chart really shows a basicity showdown. Now remember, a lower pKb value means a stronger base. So look at ethanamine on the right. It's a much stronger base than its parent, ammonia. Why? Because that alkyl group is pushing electrons toward the nitrogen, making that lone pair even more available. But then look way over at aniline, which is an aromatic amine. It's much weaker because its lone pair gets pulled into the benzene ring, making it way less available. In reality, it's all a chemical balancing act. An amine's real strength in water depends on this subtle interplay of three things: the push of electrons from its attached groups, how well water can surround and stabilize it once it reacts, and whether or not bulky groups are physically getting in the way. The final result is this delicate compromise between all these competing forces. Now, all this reactivity, it's like a playground for chemists, because each type of amine, primary, secondary, and tertiary, behaves differently. We've developed some really clever ways to not only tell them apart, but also to use them as powerful tools for building entirely new molecules.
This is a classic. The Hinsberg test is kind of like a chemical fingerprint for the amine family. You take an unknown amine, you react it with this specific reagent, and then you just watch what happens. Based on whether a solid forms, whether that solid dissolves, or if just nothing happens at all, you can definitively identify if you've got a primary, secondary, or tertiary amine. It's pretty neat.
Okay, now for what is arguably the single most important reaction in aromatic chemistry, diazotization. I know, it sounds complicated, but it's actually a beautifully precise process. You take a primary aromatic amine, like aniline, you react it with nitrous acid at just above freezing, and you create something totally new called a diazonium salt. So you might be thinking, why go to all that trouble? Well, it's because that diazonium group is what chemists call a fantastic leaving group. It is desperate to pop off the molecule as super stable nitrogen gas, N2. This makes the diazonium salt an incredibly versatile intermediate. It's like a chemical master key that can be easily swapped out for a whole host of other useful groups. And this brings us to the grand finale. We've seen the structure, we've understood the reactivity, and now we get to see the spectacular payoff. This is what brings us right back to our opening question. So instead of just replacing that diazonium group, you can also use it to connect molecules. In what's called a coupling reaction, the diazonium salt acts like a magnet for another molecule, specifically one with lots of electrons, and links them together with a stable nitrogen-nitrogen bridge. And here's the magic in action. When you couple that diazonium salt with a simple molecule like phenol, you create this new, much larger molecule. And this new structure is really special because its long chain of alternating double bonds can absorb visible light. The result? A vibrant, intensely colored compound known as an azo dye. This is the chemistry that paints our world. So when you step back, it's pretty amazing, isn't it? This one family of molecules, all derived from simple ammonia, is responsible for so much. They're in our bodies, our medicine cabinets, and our wardrobes. They really are the unsung heroes of chemistry. It just makes you wonder, with a tool this versatile, what are we going to build with them next?